Hey guys, in today's video we're going to have a look at how we can curve sketch using the different derivatives. So how can we use differential calculus to help us sketch complex functions? So the most important thing that I find that most students struggle with is which derivative do I associate with which different function, critical point in my function. So here we're going to be looking at how the first derivative impacts whether your function is increasing, decreasing, and then how that helps us to find the different stationary points and their nature. And then we're going to have a look at how the second derivative talks about the rate at which a function is increasing or decreasing, and we're going to be looking at how it affects its concavity and how we can find the point of inflection with it. All right, so the best way that we can kind of go through all these different critical aspects in a curve sketching question is by going through an example. So here we have a function f of x, which is equal to x e to the negative 2x. We're told that the first derivative is equal to e to the negative 2x minus 2x e to the negative 2x, and we want to show that the double derivative of this is equal to 4 times x minus 1 times e to the negative 2x. So if we have a look at which rule we want to be using in our function, we're differentiating this function here. I can see that this function, this part of the function can be split up as negative 2x times e to the negative 2x. Now because I have a product here, I'm going to be using my product rule just for this second part of my function here. So let's define my different variables. So we know that for we have u is equal to negative 2x, u dash is equal to negative 2, v is equal to e to the negative 2x, and v dash is equal to negative 2 e to the negative 2x. Just by using my rules of differentiation there. Cross multiplying the 2, and I have, if I want to rewrite f dash dash x based on f dash of x, I have f of x is equal to e to the negative 2x, so find the derivative of that first. So taking the derivative of the power, so negative 2 out the front, negative 2 e to the negative 2x, and then I can apply my product rule formula, which is y dash is equal to v u dash plus u v dash. So I have negative 2 e to the negative 2x plus 4x e to the negative 2x minus 2e to the negative 2x. Okay, collecting some like terms here. I have negative 4e to the negative 2x plus 4x e to the negative 2x. Pulling out a common factor, I have 4e to the negative 2x. I have x minus 1. Rewriting this the way the question gives us, we have 4x minus 1 e to the negative 2x, and that's an as required since it was a show that question. Okay, so that's how we can just differentiate to find the second derivative. So this is my second derivative function there. For part B, we want to find any stationary points. So when the question asks us to find its stationary points, we're going to be looking at when the first derivative of the function is equal to 0. So when that gradient is going to be equal to 0, it's flat, so therefore I'm going to have some sort of stationary point. The second part of the question then wants me to determine its nature. When a question asks you to determine its nature, we need to find if it's going to be a max or minimum. Okay, let's go through how we can find this. So first I want to take my first derivative, which is given to me in this question. I have f dash of x is equal to e to the negative 2x minus 2x e to the negative 2x, which is equal to 0. To solve here, let's pull out a common factor to start off with. So I have e to the negative 2x, 1 minus 2x is equal to 0. I can set both of these as equal to 0 using the null factor theorem. So e to the negative 2x is equal to 0, and 1 minus 2x is equal to 0. E to the negative 2x, so what I get there is I have ln 0 is equal to negative 2x, which I know that in my calculator I can't have ln 0, I get a math error, so therefore we have no solutions there. Looking at my other side, I have 2x is equal to 1, so therefore I get x is equal to a half. So therefore I have a potential stationary point at x is equal to 1/2. Now that's the first part done. The second part wants me to then determine its nature. So if I want to determine its nature, I've already been given my second derivative, so I'm going to use the second derivative form here. You can also use a table of values, but you're going to get the same thing. So don't use both in an exam because that's going to waste too much time. Use whatever's easier for you. This question's already given me the second derivative, so I'm going to use the second derivative method. So to use the second derivative method, I'm going to substitute in when x is equal to a half into my second derivative function. So we get 4 outside of a half minus 1 times e to the negative 2 times a half. Okay, when I plug that in, what I get is I get a negative. So I get negative 0.735 and so on. So therefore I know that this point here, that my graph is concave down. I know it's concave down because my second derivative is 0, is less than 0, which deals with my concavity. So I have a graph at the moment that's looking like this. When it's concave down, we know that this particular point is at a maximum. So a concave down graph is going to give us a maximum point. So we can say there that x is equal to 1/2 is a maximum, but we want to find the coordinates of it. So therefore, to find the coordinates of that, you'd sub in x is equal to 1/2 into your regular f of x function, which is 1/2 times e to the negative 2 times 1/2, which once we simplify that down, we get 1 on 2e. So therefore we have a stationary point at 1/2, 1 on 2e is a max stationary point. Okay, so here you get 1 mark for finding the x value or the coordinates, and you get 1 mark for testing the nature there. Okay, so that's how we can use the first derivative and the double derivative just to find the stationary points. For question, the last part here, so we have part C. It says, sketch the curve now, showing any stationary points, points of inflection, and then intercepts with the axes. So something that this question is saying is points of inflection. We haven't found the points of inflection yet, so that sounds like a good place to start. So a point of inflection is a point on the graph where your concavity changes. Now, since we know that we're working with the changing concavity, we know that we're going to be working with that second derivative there. So f dash dash x is equal to 0 is going to give us any potential point of inflections. Okay, so my f double dash x function is f4 outside of x minus 1 e to the negative 2x is equal to 0. I have, just rearranging that, I have 4e to the negative 2x is equal to 0, and I get x minus 1 is equal to 0. Once again, I get 4 ln 0 is equal to negative 2x. Once again, you can't have an ln 0, so therefore we have no solutions there. It's also super important to write this down on the page. Doesn't matter how many times you do it, or you can see it pretty early on. A marker is only going to mark you correct, and you're going to get the full marks if you show your mathematical understanding behind that. So write down that you've got no solutions there. X minus 1 is equal to 0, so therefore we have x is equal to 1 is a potential point of inflection. Okay. How can I turn this from a potential point of inflection to an actual point of inflection? Well, what I need to do is test, but I want to test for a changing concavity. So to do that, I'm going to draw up a quick table of values. I'm going to have x, I'm going to have my point 1, which we said is the potential that I'm trying to test, and then 2 points after it. So we can go 2 and we can go 0. So I'm testing my double derivative here because I'm testing my concavity. F double derivative of 0 is going to give me negative 4 when I plug that one into my calculator. We know that when we have x is equal to 1, we get 0. And then when x is equal to 2, we get a positive number here. We get 0.073 and so on. So what's happening here is we have a concave down graph, then we have no concavity, and then we have a concave up graph. So therefore, there has been a change in concavity at x is equal to 1. So therefore we know that at x is equal to 1 there is a point of inflection because my concavity is changing. So once again I want to find the coordinate points. So in my regular function I'm substituting in when x is equal to 1. I get 1 times e to the negative 2 times 1, which is going to give me e to the negative 2 or 1 on e squared. So therefore we know that 1 1 on e squared is a point of inflection. Okay, I also want to be sketching here. So I know I'm going to draw my axes. So first thing I can do is I can write where here's, let's say 1 is about here. We also have, might move that up. 1, we have a half here because that was my stationary point. So a half and my x coordinate 1 on 2e. So we have 1 on 2e being about here. We can say 1 on e squared is about here. So we know that this particular point here at 1/2 1 on 2e, that's a maximum. So my graph is going to reach that point, then come back down. And at this point here, 1 and 1 on e squared, we know that my concavity has to change. So I'm going to go up to this point. That's my maximum, so my graph is going to come back down. Then I'm still concave down, but at this particular point, I want to change the concave up, but not turn to a stationary point. So what's going to happen at this point is you're going to go down like this. Because if I have a look at this particular point now, this graph here, if I was to draw a parabola, I'm now concave up, but on the other side, I'm concave down. So that's a change of concavity. You can kind of see here, my function's actually going to approach infinity. Okay. As x approaches infinity, my function's going to approach 0 there. All right, so that's how we would graph that one. I know it says sketch any intercepts with the axes. We only have the one at the origin here, like that. All right, so that's how we use all the different derivatives in calculus. Hopefully this one helps. Just remembering the things that I mentioned at the start of the video. So first derivative, we're looking at stationary points, and then second derivative, we're looking at concavity there. Okay, so hopefully that one helped.